Let's go to the next question, again from Kamini. It's about device tree. What is the purpose? How is it used? Okay. So there are two types of devices. One, you can say discoverable and non-discoverable. Right. So the USB, for example, is discoverable device, PCI and all that. Like we discussed earlier, how the discovery happens. Non-discoverable devices, basically like I2C, SPI, etc., GPIOs, whatever. These are all very popular in the SOCs, and they are not discoverable. So the system developer, designer has to provide the interface information for this. Whereas these are discoverable basically because the device self-advertise their capabilities, their requirements, and how to handle them, how they are to be handled. So that is the easier part. So many of the SOC devices are non-discoverable. So the question is, how do you actually tell it in an OS independent way, or in a, basically through data rather than code, right? So basically, more important is their interconnect. How are they connected to the CPU system, right? That is the most critical thing. What happens is there are three ways you can do traditionally. So the three ways to deal with non-discoverable systems. Apologies for my handwriting. One is that you could have it embedded in the code, which code, the bootloader code, for example, or BIOS code or whatever, application code, etc., OS code, and so on. So basically, it is not portable. It's very tightly coupled, and but that is the minimum you can do. Basically, you write code for each kind of interconnection that you have. And so what are we talking about interconnection here? Basically, if, let's say you have a device like SPI. Okay, you know the basic lines. So you will probably have a clock. You will have so this actually describes only three lines, right? So the slave to so in one direction, in each direction. But apart from this serial, there are non-standard interfaces. For example, what IRQ9 it will be using, and how do you do say slave select? So basically, if you have multiple slaves on the SPI bus, the slave select is normally done by a GPIO line, right? So you would use actually GP output line to address. So these are outside this definition of the SPI. It is basically specific to a hardware platform. So you need to capture this for the driver to be able to correctly operate on a given platform. Similarly, if you have a 3-wire UART, you have basic lines, but then you if you want flow control, so the flow control is done again through GPIO and so on. In fact, even the 3-wire UART, the data lines, the RX, TX may also be using a GPIO line. So basically, you would have to capture this information in some form. You could directly embed it in code, or you could put it in a nice data structure. The question is, where is the data structure? So let's say it's there in a data structure. Now the question is, this is basically C, let's say C data structure. It has to be compiled and linked. The question is, do you link it with the bootloader, the OS, or any other application directly? That means the OS, etc., have to be recompiled for each configuration that you have with this C data structure, which is not very nice thing, and you may add later on in the life cycle new devices, etc. Or you may change the OS. It's a big pain. So you need a different, better way to do it. Now, what we do is, there is in the BIOS world, there is some other technique. Basically, it is taken care of a BIOS on the x86 at least, using what is called ACPI tables. So the BIOS takes away the dependency, but it is C code, and you have to build the BIOS for that platform, which is reasonable in the PC world. But then the OS is shielded from this data, but then you are actually, changing any hardware, anything is not possible. The better way, so, is basically device tree. This is the norm today, both in ARM-based embedded systems and maybe, I am not sure, but x86 systems as well. So what is device tree? So you describe the hardware device interconnects in a text file. So there is a specific syntax for that. Think of it like an XML configuration or a JSON kind of configuration, right? So basically, you would say what is there on the platform. So let's say you have a dual core processor. So there is, let's say, Cortex A7 Core 1, Cortex A7 Core 2, and then you may have very many controllers. You may have a USB controller, you may have DDR RAM controller, and you may have, let's say, I2C controller, and so on. And then the I2C controller may have also, let's say Ethernet, and so on. They will connect to the actual hardware, Mac, and this I2C will connect to, let's say, an audio device or your codec, and of course this will connect to an SD-RAM. So this is basically the hardware, how they are connected. So the device tree source file, what is basically a DTS, will try to capture this information in a particular syntax. I am not going to go into the syntax, but it generally says something like CPU. You can give it a name, CPU 0, CPU 1, and then you describe what kind of clock it will run, and entry, whatever address, and so on. So similarly, you will have one entry for I2C, one entry for ATH, or one per device on the platform, right? So this basically describes that particular device, what is the clock, in this case of CPU. For other things, it may have other information. Basically, whatever information is required to, for example, for the I2C, etc., what IRQ line is used. For a DMA, again, IRQ, sorry, for ETH, it may use IRQ, DMA channel to be used, and so on. So basically, it is capturing the hardware, whatever the schematics tells you, in the form which is human readable, and basically it's a syntax notation for standardizing this description. So that is what device tree source is. Then what happens, assuming you have a device tree source, so you start with the device tree source, you run it through a device tree compiler, it will produce a binary, so which is machine readable form. So it is called a blob. So it is a .dtb, it's a blob. Now this blob, so you don't have to worry about symbols and things like that. So it is not necessary to, the idea of this is not necessary to link or recompile and things. So once you have a blob, you can, as much, this is a binary thing, you can pass it on to the kernel of a particular OS. It can be passed on to a bootloader as an object. So basically a blob is an object which can be uh, given to this kernel or bootloader, and so that way it is a runtime facet. So no need to recompile, link, etc. the bootloader or the kernel for this particular changed configuration. So you just go edit the DTS file, compile it, create the blob, and then give it to the bootloader, etc. So basically, it is just a binary representation of this. Now, how do you handle that? How do you actually hand over that? So if you think of it this way, the bootloader um, basically loads the kernel image, and then it passes the DTB. Um, so basically, it loads it onto RAM and then passes the address to the kernel. So if you think of the memory like this, you have the RAM, so the kernel image, and then somewhere you have the blob. Now, so this address, this is a kernel entry point address. So it is basically the kernel address and the blob or DTB address. So the bootloader knows both these addresses. So it just has to tell the kernel where the blob is. So it is done basically using the uboot command. So you have the uboot command, which you can use to pass this. Basically, something like boots, and then you say kernel address, where to load the kernel, and the blob address or DTB address. So this is how you will tell. Now, how does the kernel get? So this command, what it does is it uses the DTP address. So it does two things. It loads the blob, it loads the kernel, and then somehow passes the DTP address to the kernel. In ARM processors, typically this is standardized. It is a particular register is used in each case. Particular register, CPU register, is used to pass this DTP address. In the case of ARM 32 architectures, it is passed in the register 2. So that's done. Basically, you have told the kernel what the device description is in a binary form. What the kernel will do is that it will parse the DTP, okay, and extract whatever the data or information there regarding the interconnections of the schema, of the platform, hardware platform, and then appropriately set up its driver. Okay, so the parsing, there are libraries like lib, I'm not sure, libfdt or something like that. So just like you have JSON parsers, any other parsers, there is a library component for device tree parsing, which can be used to actually parse the binary blob and extract the information, and then you're all done. Basically, what you're done is instead of compile time binding to a particular hardware platform and its device interconnects, we have done it at the runtime. That's all the purpose of device tree is. Okay. Now, why is it called tree? We talked about this platform having CPUs and then having I2C. You may have other things which are basically hardware. For example, the interrupt controller may connect to many of these devices. So basically, a .dts file will have a node per hardware unit. Unit here maybe the PIC, I2C, etc. And then somehow you have to say how they are interconnected. So there is a basically a pointer kind of thing. So it's a reference or whatever, it is basically the node, and then you will say, okay, let's say there's a child node, and then there may be many child, so you may link the child nodes. So this is part of the syntax. So in the blob, in the DTS, we talked about the information. So there are two kinds of cell information, number of cells, and you also have the pointers to the parent or the child node or next child node and so on. So basically you can map the hardware hierarchy into a descriptor. So that is why it is called a device tree. But once the blob is created, it is flattened so that it is uh, easy to manipulate. So the parser after that, the DTB can be flattened. It can be flattened earlier also. So the input is in a tree structure, reflecting the hardware hierarchy, and the binary version is a flattened thing. Basically, it can be directly manipulated without having to traverse all this. So that's basically all I know about device tree. You have any questions, Kamini?
No, Raghu.
Subhash, I'll unmute you. Yeah, go ahead, Kamini.
I have no further question. Thanks a lot, Raghu. I mean, it was a very good explanation.
Okay. Subhash, you want to make a comment?
No, I was, when you were mentioning what goes into device tree node, like one of the most important, like if it's a controller and all, we need address, right? So the memory map address, that also goes in there. But,
absolutely. Yeah. Anything you need to be able to control the device. There is what? Basically memory map of the register. So everything is passed through that in runtime. So conceptually, it is basically how do I do it data driven, and how do I do it without using symbols. So you need a standard way of structuring that. So that is all that standard is.
Hey Raghu, this is Bhargavi. I have a question about the ACPI tables. Could you elaborate a little bit more on the BIOS?
I'm sorry, I'm not too familiar with that. I just know it exists. I'm not from the BIOS world, so I'm not sure.
Okay.
Sorry about that. I will try to read up. If I find something, I can pass it on to you.
Sure, no worries.